Welcome to Combustion 101, Combustion Principles and Safety Testing. I'm Jim Bergman, co-owner of TruTech Tools, and this seminar is going to walk you through the basics of combustion analysis. TruTech Tools, a little bit about us. We're experienced professionals. Bill and I have been partners in TruTech Tools for about 4 years now, and we offer CEUs and training to the HVAC and related trades. Between us, we have a little over 45 years combined experience, and we'd like to bring that to you in practical, related, and hands-on training. And one of the great things is on these seminars, you can earn while you learn. So if you're BPI and you need the CEUs, you can get those at the end of the course. If you desire the BPI CEUs, you got to give us your full attention. So you need to refrain from surfing off to other screens. Interaction with the instructor is required, so make sure you text me a question. Everybody's going to be on mute during the session, but make sure you text me a question over. And your BPI number should have been entered at the time of registration. And if you didn't do that, don't worry, just send an email over to Marilyn at TruTechTools.com with your name and date of this webinar. Our agenda tonight, we're going to go over the combustion process. Understanding combustion efficiency and combustion, common causes of the CO and related safety, how to perform a complete combustion analysis from start to finish, ventilation air testing, or worst case testing as some of you may know it, heat exchanger examination and testing, a little bit on field modification and field setup of the equipment, and we're going to go over how to measure the appliance output and thermal efficiency. We also have our hidden agenda, which we've chosen not to reveal. And now we're going to start off with really why is combustion analysis important. And you know, a lot of people miss probably the most important thing is verification of safety of the appliance before we service it and after we service it. We really want to know when we walk in the door, is there a problem? And when we left, did we create one? So we really want to check the appliance test in, test out. And also we want to test it, you know, before we weatherize a home, and then we want to test it after the weatherization work is done. We want to calculate the combustion efficiency and see how the appliance is operating. We want to monitor the appliances, the appliance for pollution. So we want to see, is it producing NOx or is it producing CO? We want to verify conformance with the manufacturer's guidelines, and we want to try and minimize any warranty issues and assure the equipment longevity. Combustion testing results, you know, what they tell us is a lot of things, and it comes down to, are we saving money? You know, and it's going to save us time because we're gonna know the appliance is operating right the first time on the first call. We're going to avoid those callbacks. We're going to limit our liability. You know, we're going to make sure that the appliance is safe when we leave. We're going to maintain the equipment warranty. We're going to provide confidence, and not only confidence to the consumer that their appliance is safe, but also confidence to the technician that when they leave, they know the appliance is operating safely, and it gives you a little comfort as you go to bed at night that you're not leaving somebody in harm's way. It's going to provide increased comfort because we're going to make sure we get that maximum BTU out of the appliance. We're going to get increased safety because we're going to make sure it operates not only safe under normal conditions, but under worst case conditions. We're going to increase the energy efficiency, and we're going to lower our environmental pollutants. When we talk about basic combustion theory, what a lot of people don't realize is combustion is just a chemical reaction of rapid oxidation, and it started by the correct mixture of fuel and oxygen and a ignition source. When we talk about complete combustion, there's a couple things here, and by the way, if you took the class yesterday, there's a little bit of overlap on the first few slides because there's some basic information we want to make sure that we cover. So then we'll get into some new content really quick. But when you look at this slide, the key thing to pay attention to is this is oxygen, fuel, and heat. Okay, when we're talking about complete combustion, we're talking about the complete conversion of the carbon and hydrogen in the fuel to heat, carbon dioxide, and water vapor. And carbon dioxide, same thing we exhale, right? We're not talking about carbon monoxide, but carbon dioxide. That's where we're going to get that maximum heat content out of the fuel. So we're talking like natural gas, you're talking like 1,050 BTUs, right? 1,050 per cubic foot. But it's oxygen, fuel, and heat. In reality, when we get out in the field, this never happens because air is used for the oxidizer, not oxygen. So this perfect combustion, and we talk about theoretically perfect combustion, can never be achieved. When we're looking at it from this standpoint, when we have air coming in, we get oxygen and nitrogen. We have, and plus like 1% other gases. It might be argon, helium, could be refrigerant, could be, any other gases that are in the air in that combustion zone. Could be even like chlorine, things outgassing, formaldehydes, aldehydes, things in the home. We get that fuel, which is our hydrogen and carbon, and our heat source, a small spark to get this thing going, spark or a pilot or something like that. The output side of that is heat, and we could get some soot, especially if we have things like fuel oil and we get incomplete conversion of carbon to carbon dioxide, CO2, possibly carbon monoxide. Sometimes we produce it, sometimes we don't. Air, excess air, because some air goes through the combustion process unused, and we have water vapor, and then we get some toxins like NOx and SOx and acids that are also in that flue gas. And this is really when we talk about standard combustion or the combustion we deal with day to day. This is what we typically get out of it. The source of toxins. Everybody goes, well, what's the source of toxins? Well, chemicals in your house outgas. Chemicals in the combustion air zone outgas. So we're talking about things like chlorine bleach, salts, dryer softener sheets are probably one of the worst ones. Household chemicals, paint thinners, gasoline, kerosene, anything that would be in the area of the combustion air zone, a CAZ, you'll hear that term a lot. It's CAZ's combustion air zone. If the appliance is using the air in the space to burn for combustion, any of those chemicals, even if they had lids on them, can outgas through the plastic, can outgas through the tops, and can get into the combustion chamber and cause the heat exchanger to literally rot out, and also causes some other chemicals in the air. Especially if we're talking about ventless heaters, which a lot of people are recommending you remove today, simply because the outgassing of other chemicals in your house and the byproducts of combustion that it does make. So, they do have their place, and I'll tell you right now, I still use one on my porch because I have plenty of fresh air for it, and it works great as a porch heater, but it's not intended to be a primary source of heat. So when we look at the combustion process, what we're looking at is CH4, 4 cubic feet of methane, plus 3 cubic feet of oxygen, and a spark to get this thing going. It's going to give us heat, 2 cubic feet of water vapor, a cubic foot of carbon dioxide, and a cubic foot of excess air. Okay? And that excess air is one of the primary concerns. We're talking about efficiency of the combustion process. Excess air is one of the primary things we're concerned about. The heat energy we're going to produce is about 1,027, 1050 BTUs, and that can vary anywhere from about 925 to 1050 with these. It really depends upon the heat content of the gas that you're getting. That 2 cubic foot of water vapor is pretty significant when you stop and consider how much water a typical furnace produces, and obviously a cubic foot of carbon dioxide. The problem with air is because we're using air as the oxidizer in the combustion process and not oxygen, again, we can't ever get that perfect combustion. And huge amounts of heat energy are absorbed by that nitrogen in the air, which plays no role in the combustion process. So, when we're looking at a typical gas furnace in your basement sitting there and it's using, air as the oxidizer for combustion, it's pulling 79% of that is nitrogen. That nitrogen goes through. We got to heat it up coming in, and that heat goes right back out the chimney, and it's effectively just all standby losses. I mean, it's not standby losses, but operational losses. And there's, because we're not using oxygen like we would with like an oxyacetylene torch as the oxidizer, it's just a function of the product design, and so we want to really minimize the amount of excess air going in the combustion process. And there's two things we're going to look at, and we'll get to them later, but we're looking at the roles of efficiency and safety, and so that's what our primary concern is. We're talking about composition of the air. Again, it's 20% oxygen, 20.9% oxygen, 78% nitrogen, 1% other gases. But here's what you need to know about that. In order to get that 2 cubic feet of oxygen we need, you got to have 10 cubic feet of air is required, because the air is basically 1/5 oxygen. Why do we care about that air? Well, we got a couple reasons. Because we're using that air for ventilation, for infiltration. Ventilation is basically the total air brought into the house or structure. Infiltration is unintentional air brought into the structure. Combustion air is air we're using to burn, and dilution air is air that we're using to actually dilute the flue gases that are going up the stack. And the danger is all the things that are competing for this air. Typically we don't always consider that the fact that we have an appliance that's using large amounts of air that's in our house, and we've got to bring in air from somewhere to replace the air that we're exhausting out through the venting system. Airtight homes, we're taking and we're sealing up a lot of these homes today, especially if you're involved in weatherization or BPI testing, where we're going out and trying to fix problems in homes that are construction issues. But as we're fixing this stuff, you may be fixing one problem, but maybe creating another. Negative pressure conditions in homes or commercial buildings can create backdraft to the appliance, especially if we're talking atmospheric pressure appliances. But it can even happen with sealed combustion appliances. And I've actually seen sealed combustion boilers backdrafting in mechanical rooms simply because the negative pressure in the equipment room was overcoming the seals and the doors on these boilers. And so, even things in a residential home like a common exhaust bath fan can compete with the normal venting process of combustion appliances. So let's just recap here a little bit what the airs were, just to make sure we're all on the same page, because when we get into the building science industry and the HVAC community, sometimes there's a little bit of discord in the terminologies that's used, so it's real important we're all on the same page. And when I'm talking about some of these terms, we understand exactly what we're talking about. Ventilation air is the total air, which is a combination of the air brought in from inside and outdoors and air being recirculated within the building. That's sometimes used in reference, and sometimes it's used in reference to only the air brought in into the system from the outdoors. Typically, however, the industry refers to ventilation air as indoor and outdoor ventilation. So we're talking about ventilation air. If you're talking about a hot water tank that's atmospheric draft, the ventilation air is the total air that's in the house that's available. If we're talking about a sealed combustion appliance, well, ventilation air, it's the air in the outdoors used for that same process. Infiltration air is a term used to describe the outdoor air that enters the building through cracks or unintentional openings. This is what weatherization is trying to fix, right? We're going around sealing up the windows, sealing up the doors, putting in new, sealing unintentional bypasses through a home or through a wall. Infiltration air is air that comes in through places we don't really want it to come in through. Just like, if you're playing football and somebody infiltrates your line, somebody you don't want to get through. So that's what we're looking at with infiltration air. We're talking combustion air. We're talking about air that's brought directly into the combustion chamber of the furnace, supplied from in the basement or from the outdoors. But combustion air is the air needed to burn the fuel. If we don't have oxygen, we don't have a flame, and you got to have all three parts of it for it to work. And dilution air is our air that enters the draft hood or draft regulator, mixes with the flue gases. This is after combustion has taken place. And on modern furnaces now, however, typically you only think of dilution air as the air that goes up to the draft hood. But on some of the modern furnaces, it actually also goes right through the combustion process, and it's also measured as excess air in the stack. You'll run across some 80-plus furnaces, especially if you get into ream furnaces or some of the other manufacturers tend to do this. They'll actually run 150% excess air. And what that means is you've got 150 times the amount of air you need to support the combustion process. But some of that air is actually diluting the flue gases. It's drying them out so that condensation will not occur in the flue gases and in the chimney. So how much air do we need? Well, there's 1 cubic foot of natural gas requires 10 cubic feet of air for perfect combustion. Okay, so for every cubic foot of net gas, we need 10 cubic feet of air. We typically supply an additional 5 cubic feet of excess air to assure safe combustion, right? And what we're doing here, when you think about the gas and the fuel mixing together, imagine you got 100 blue marbles and 100 red marbles in a jar, and you shake up the jar. What are the odds of a blue marble and a red marble touching together on every single marble, right? The odds are pretty slim. So if we increase the amount of blue marbles, and the blue marbles in this case would be the air, you know, we put in 50% more blue marbles. Well, the odds of a red marble contacting a blue marble now when we shake that jar up are much higher. And that's what excess air is basically for. It's extra air through the combustion process to assure complete conversion of the carbon to carbon dioxide in the flue gases. Now, if we have a draft hood, like a conventional draft furnace, there's an additional 15 cubic feet of air required for dilution. So, and that 15 cubic feet of air is going up that chimney 24/7, 365. So for every, you know, for basically going to look at it for on a residential furnace, you know, for every hour it runs, for every cubic foot of gas it requires, it's running 15 cubic feet of air up there 24/7. So you're talking about a tremendous amount of air going up the chimney all the time. So at the end of the day here, we're looking at somewhere between 15 and 30 cubic feet of air per cubic foot of natural gas used. So let's break this down a little bit further. Let's say that we have, you know, a heat content of gas of 1,000 BTUs per cubic foot, just to make the math simple, right? And we multiply that 100,000 BTUs per cubic foot of gas times 100. That would be equivalent to a 100,000 BTU furnace. That's line 2 right there. So what we said is there's 100 BTUs, or 100 cubic feet of gas, right, required per hour of operation. So if that furnace had a dilution air hood and we had 30 cubic feet of air required per cubic foot of natural gas, well, 100 times 30, that's 3,000 cubic feet per hour. If we're talking a 24-hour day, that's 72,000 cubic feet of air per day, or 30 CFM a minute of operation. And that air's got to come from somewhere. And a lot of times we're not considering this when we're sealing up all the infiltration spots on a home. So we got to make sure there's enough air for combustion and safe combustion. Now, when you look at your combustion analysis, when we're doing a combustion analysis, you know, we get to efficiency. And the efficiency is calculated by the combustion analyzer. It's actually a modified equation that considers combustion efficiency and stack losses. It's part thermal and part combustion efficiency. If we were actually talking about pure combustion analysis as a science, we would actually be measuring the combustion efficiency right at the flame, right? Because we would want to see how much fuel, how much gas mixed together, you know, how much air came out, how much fuel came out. We would do it right at the flame. We're not. We're actually doing the testing at the stack. So we don't know how hot that flame got. We don't know how much heat that flame produces. But what we do know is how much we lost. We're losing up that stack. And so that's what we're doing. It's a modified equation that is very representative of the efficiency of the appliance that we're testing. And it actually does two calculations on most analyzers. One's called a dry gas calculation, which is for a non-condensing appliance, which means it's going to calculate the amount of heat energy that's you know, going up the stack, including the heat loss of water. And then the other one, when we get down below the dew point temperature of the flue gases, it also considers the energy we got by removing the additional latent heat out of the flue gases. If we look at a standard combustion diagram, what we've got here is a stoichiometric line. And the stoichiometric line is where perfect combustion would occur. When you're on the stoichiometric line, if you're burning a fuel, you have no excess air and you have no excess fuel. So you have perfect proportions, air to fuel, and all of it's burned up. When we, on each side of that graph, we would put the incomplete and complete combustion at the top, right? So if we're to the left of the stoichiometric line, we have incomplete combustion. We're to the right of the stoichiometric line, we're going to have complete combustion. On the bottom there, you'll see I just added in excess fuel and excess air. So on the left, we have incomplete combustion. We got fuel that's going through the combustion process, not being used. If we go to the complete side, we're consuming all the fuel, but we're using a lot of excess air to do it. Or, well, maybe a lot, maybe a little, depends how much excess air we have, but we do have excess air. Now, if we graph our O2 line, you can see it starts at the bottom, and basically, the more oxygen we have, the more excess air we're going to have in this little equation per cubic foot of gas. And our CO2, obviously on the stoichiometric line, we're going to get the ultimate conversion of carbon to carbon dioxide on the stoichiometric line. So that would be perfect combustion. And here's an interesting one though, CO. CO could be produced on either side of the stoichiometric line because we don't always have enough oxygen. This goes back to the marble examples, right? When we have right amount of fuel, right amount of air in combustion, we may not get a molecule of carbon attached to a molecule of air, and we have excess carbon going through that's unburned. So we actually have to supply some excess air to the combustion, and until we get enough excess air in there that it actually consumes all that carbon, we don't get complete conversion to carbon dioxide, and we get CO in the flue gas. So you could actually have excess air and carbon monoxide at the same time in the flue gas. It's completely possible until we get enough excess air that every carbon molecule attaches to an oxygen molecule. If we look at the top of our efficiency line, our peak efficiency, when you engineer appliance, the peak efficiency is actually to the right of the stoichiometric line. We're talking about peak combustion efficiency for this appliance. So when we look, and if we had smoke, like an oil appliance here, we can get smoke on the excess air line also, and the smoke is simply unburned oil in the flue gases. Ideally, the ideal operating range for burners is typically a trace of smoke. We're going to have some excess air. We're going to have almost complete conversion of the carbon to carbon dioxide, and that's going to put us at our peak efficiency. All right, so we're going to go over a little bit more on what these numbers mean, but this is just like an overview of combustion. The combustion analyzer itself, it's only got a couple cells in there, and a lot of people don't understand what that thing does, but here's what it's doing in a nutshell. The analyzer uses the oxygen and the net temperature measurements of the fuel. So it pretty much knows how much oxygen's coming out the other end, and that's going to help with determine the combustion efficiency. When you tell it what the fuel is in the analyzer, you tell it it's natural gas, it goes off a predefined heat content for that gas. So it's looking at, okay, well, how much heat did that gas develop? How much heat's going up the stack? How much oxygen's going up the stack? And it's giving us a reading on the analyzer. So, in a nutshell, that's all it's doing. And it's got a second sensor in there that's your carbon monoxide sensor that's, we're using to determine safety. The efficiency equation is a very reasonable estimation of the steady state operating efficiency of the appliance. Again, some analyzers perform a dry gas calculations only, and then some estimate the latent energy removal. Now here's what you need to know about this. It's absolutely impossible to determine the amount of latent energy removed without measuring the volume of condensate produced. Okay, and this goes back to a little bit of basic science for you, but just in a nutshell, you could have 212-degree water, or you can have 212-degree steam, right? So if we take a pot of water and throw it on the stove, there's energy that goes into converting the water to water vapor, or converting the water vapor back to liquid water, and it's energy to the tune of about 970 BTUs a pound for water condensed. We know with gases, once we get below the dew point temperature and we know we're condensing, we don't know, though, how much we're condensing. So when we say it's a reasonable estimation of the steady state operating efficiency, we know how far we are below the dew point. We know we're removing moisture. We know the further we are below the dew point, the more moisture we're going to remove. But is it a scientific perfect measurement of the amount of heat coming out? No, it's not. It can't be, because we can't measure that volume of condensate. The combustion efficiency measurement is really combustion efficiency minus the stack losses. It's not AFUE. Okay, it's not annual fuel utilization efficiency. The number will be very close to the AFUE, but it's reflective of that, but it's not a true AFUE measurement. That's done in a completely different way. It's not the thermal efficiency, and it's not COP or SEER. So, well, what does it do? Well, first of all, let's look at what's measured. We're measuring carbon monoxide, and Carbon monoxide is a dangerous byproduct of incomplete combustion. It measures the stack temperature. We call it gross stack temperature because it's the temperature of the flue gases plus the combustion air temperature, right? If the combustion air comes in at 70, obviously it's got more heat in it than if it comes in at 0, right? Because we're going to, instead of heating up 70-degree air, we're heating up 0-degree air. You know, that air is colder, right? We're running, 79% of that's just nitrogen going through the flue gases. So, you're bringing air from outdoors and you're heating that air up. Now, you got to realize that the specific heated air is 0.24. So, I mean, it takes very little energy to raise that 0-degree air up to the stack temperature. So you're not talking about like huge losses on a 90 plus by bringing the outdoor air from the outside. In fact, the gains are actually much better because you're getting a better concentration of oxygen, and we're getting clean combustion air, which makes a big difference in the longevity of the appliance. So that the gains far outweigh any small loss we'd have with a cooler combustion air temperature. And we're could be measuring NOx or NO. And that's typically something we'd measure like in California where they are monitoring pollutants in there. But these are mononitrogen, monoxide, or nitrogen monoxides. They're all pollutions. So what's calculated? And oops, sorry about that. Well, the analyzer calculates the efficiency, which is a calculation of the maximum available heat in the combustion process minus the stack losses. It calculates the NOx, which is a mixture of like nitric oxide or nitrogen dioxide or trioxide, and it calculates your CO2. They don't measure CO2, they actually calculate CO2. The carbon dioxide is just a byproduct of normal combustion, but it is considered a greenhouse gas. Excess air is calculated, and that's the air that's passing through the combustion process without acting as an oxidizer in the combustion process. And a certain amount of this is usually required to assure complete combustion. The excess air dilutes the flue gases, so, in most cases we want to keep this to a minimum to keep the combustion efficiency at its maximum. A certain amount of excess air is required for safety, and some furnaces it's also required for dilution. CO air free is a calculated measure of the undiluted CO in the flue gases. And this is one of the most important measurements. There's two measurements your analyzer is going to make with CO. One CO and the other one CO air free. The only reason that we look at a raw CO reading on a combustion analyzer is to protect the CO cell. We don't want to overrange the cell. CO air free is an apples to apples calculation, right? We're talking about parts per million. So if I, if I have a million parts of something and I throw 3 parts, in of CO, well, there's 3 parts per million, right? And obviously we could dilute that if I put more air in there, and that's what at one time manufacturers were doing. The furnace would produce 400 parts per million CO, so let's just add more excess air to it. That'll dilute the CO, and the parts per million will go down. Well, what the problem with that is it doesn't tell us how much CO, if all that gas went into the space, the same volume of CO would go into the house as it was before, and obviously that's going to cause the same problem. So we went to a CO air free measurement, which is now it's saying apples to apples. If we take the oxygen dilution out of the equation, how much CO is actually in the air? And this is the one that we care about. This is what all the standards are written on. The dew point is the temperature below which the water in the flue gases will start to condense, and that's again a calculation. We sort of care about that too because if we're talking about a non-condensing appliance like an 80+ furnace, we don't want it raining inside the chimney. And if we can measure the temperature of the flue gases exiting the chimney, let's say that the dew point's 100 degrees, or let's say maybe 150 degrees, and we get up to the top of a brick chimney and the flue gases are coming out at 90 degrees, we know that it's raining inside that chimney, that the flue gases have dropped below the dew point temperature, and those flue gases are going to start to condense. So what do we care about at the end of the day? Well, aside from not leaving a giant mushroom cloud behind in your rearview mirror when you're driving away from the home, what we really care about is, we call it SCCE, We're really concerned about safety, being in compliance with the manufacturer. It's consistent. It consistently does all this, what it's supposed to do, and we're concerned with efficiency. And I'll really going to spend some time on consistency because that's probably one of the most overlooked things in combustion analysis. So let's talk about, first of all, safety and understanding CO and how it's produced. And we're going to talk about a couple things with CO, ambient CO testing, ventilation air testing, stack CO testing, and then I want to talk a little bit about pressure switch cutout settings on power burners and things that have adjustable pressure switches. Pull this out here. Sorry, I had the questions minimized, so let me make sure I hit some of these here. It's come on, maximize this thing. All right, so what is carbon monoxide? Well, CO originates from incompletely burnt or oxidized carbon in the fuel. And it's extremely dangerous for human and animals because it prevents absorption of oxygen in the blood. Your body basically cannot tell what's oxygen and what's carbon monoxide. So basically what it starts doing is replacing all the oxygen in your blood with CO. And eventually you end up with CO in your blood, no oxygen in your blood, and you go through oxygen deprivation. And your organs start to shut down. Your organs start to die. Reasons for formation of CO are typically a rich fuel mixture, improper venting, and that can result in like recirculation of the flue gases. Flame impingement. If you look at that, actually look at that burner right there, the left-hand side burner. You'll see the flame is overblown against the heat exchanger. It's actually got a crack in the heat exchanger, and the burner right next to it on the right, the flame's like straight up and down the way that it should be. That flame is what's called flame impingement, and also burner alignment. You know, there's a lot of things that can cause it. We're going to hit some of those in detail. All right. So some characteristics of CO. Well, CO is odorless. Can't smell it. It's colorless. We can't see it. It's tasteless. So you're not going to really have no idea it's there. And it mixes really well with the air. And what that means, it doesn't stratify. The CO will follow the airflow in a structure, however. So let's say we got a furnace and spilling in the house, right? And the flue gases are hot. Well, those hot flue gases, they will float to the top of the house. So you might detect CO at a ceiling. But as soon as those flue gases mix with the air and cool down to room temperature, that CO is going to pretty much follow the air currents in the structure, and it's going to like mix evenly throughout the structure. And it's not going to, we're going to get this nice even mixture. So you could die on the floor just as easily as you could sleeping in a bunk bed. It's going to mix in very well, and the flue gases will cool off very, very quickly. So you're not talking about, you're going to go up the ceiling and find 200-degree flue gas at the top of your ceiling in your second story of your home. Not going to happen. They're going to be back down to room temperature before they ever get that high. And CO is obviously poisonous. We talked about that. When you get symptoms of CO, persistent headaches, dizziness, blurred vision, nausea, fatigue or drowsiness, shortness of breath, confusion. People can get coughs that go on forever. They could get tired. They're feeling ill at home, but they're fine upon leaving the home or the building. These are all questions, if you think you've got a CO-related poisoning or somebody's getting ill from that, a low-level CO poisoning, these are all questions you should be asking the consumer about, are they having these symptoms? How big is a ppm? Well, I discussed this just a second ago, but just to give you a visual on this, 1 ppm is about the size of a drop of oil in a 5,000-gallon pool. So we're not talking about very big. 10,000 ppm is 1%. Okay, so 1 ppm is 1/10,000th of 1% by mixture. So it doesn't take a whole heck of a lot of CO to cause major problems in the home. The CO is a cumulative poison. It actually builds up in your bloodstream. Remember, this is replacing the oxygen in your blood. So it's not like you have to, we're only worried about large amounts of CO. We're worried about any CO because it's going to build up over time in our blood. The U.S. EPA and Health Canadian 8-hour exposure limit, they don't want to see anything over 9 parts per million, 9 to 13 parts per million. Now, they got to realize there's all kinds of standards. We're going to talk about BPI standards, and these are just some that are up there for, for Canada, U.S. EPA, OSHA. There's all these different standards, but there is no law on CO. I mean, our whole industry is governed by standards, but there's nobody out there saying that this is the maximum amount that you can have. There are industry standards, and the standard says if you're going to follow our standard, like the BPI standard, this is the maximum amount that we're going to allow you to find in a home and permit you to do weatherization or permit the furnace to keep operating. But what you're talking about is what we call a reasonable standard of care, right? So let's say you end up in court somewhere. What they're going to look at is, well, what are the industry standards? This person had 400 ppm of CO in their house, and they're going to look at, well, there's no standard that would allow that. They can look at the building standards, building code standards. They could look at BPI standards, the ASHRAE standards. They could look at ACA standards. Anybody that writes standards out there, and they would say, well, obviously this guy didn't follow a reasonable standard of care because the industry standards say this is what he's supposed to do. And so this is when we follow an industry standard like BPI or like ACA or like ASHRAE standards, we're following a set of guidelines. And which standards you're following depends on what industry or segment of industry that you're working in. But a couple interesting things here. If you get into that 200 ppm range, you're going to get a slight headache within 2 to 3 hours. And again, it's cumulative. So being in that CO range for a while, it's going to cause some pretty serious effects beyond that. At 400 ppm, you're going to get a slight headache within 1 to 2 hours. At 800 ppm, you're going to get sickness and twitching of limbs within 1 to 2 hours, unconsciousness within 2 hours. At 1600 parts per million, you're going to get a headache within 20 minutes and death within 2 hours. And we get up higher, you can see that we just get closer and closer and closer to dying as we go. I'm going to pull these things over here. I'm having a little trouble getting these questions where I can see them. I apologize. I'm going to move this box over and see if I can get it up any bigger. For some reason it shrunk them. All right, had a couple of questions here. I'm just going to hit real quick. We will have copies of the slides when we're done. And are you saying no soot of natural gas or propane? You can get soot with natural gas and propane. Typically not. Typically, if we have soot with natural gas or propane, we got way too much fuel and not enough air. But under normal conditions, never any soot with those two gases. Typically, we'll have a little bit of soot with oil. The 327, 330, whatever combustion analyzer you're using, it actually watches stack temperature to determine whether it's in the condensing range or not. And you can also set up the analyzer, like with the 330, we can actually set up the analyzer to tell it that it's a condensing appliance or non-condensing appliance. But typically what we're talking about is stack temperature that determines that. And I had a couple questions on CO air free. BPI wants CO air free. That's correct. There's no way with a raw CO reading to tell what your ppm, what your parts per million is. And let's just visualize this for just a second. If I've got a cup of water and I've got a gallon of water, and I put a drop of oil in each one, right? I have the same drop of oil in each reservoir, but they're two different sizes, right? But the proportion is completely different, right? I have a gallon in one, I have a cup in the other. Both have the same drop. That drop represents the CO. right? That's what we're concerned with, because when the CO mixes with the ambient air, when it mixes in eventually, that same drop is going to end up in no matter whether we have the gallon of excess air or we have the cup of excess air. So we need to be concerned with CO air free, because CO air free is going to give us an apples to apples comparison of saying when we take out the dilution out of the equation, how much CO is actually in the flue gas. And that's what CO air free is, the standard. If you were taught the other way, it's wrong, because it's giving you a raw CO reading, which is absolutely valueless for understanding how much CO is in the air. CO air free also applies to ovens, and so that's it. All right, I think that was all the questions. I'm scrolling down as we go, and I'll try and get them here. I still haven't got this thing for some reason to expand out. I'm not sure what in the world it did, but we will work our way through this. All right, back to the slides here. When we talk about carbon monoxide concentration versus time, right? A lot of the testing was done by actually looking at stuff in the military. And this graph here, it basically shows you that the same levels of CO, and you look at like down the left-hand side here, it's parts per million of CO. And at 400 parts per million, right, we're looking at, and by the way, COHB is how much CO is in your blood, basically. Right? What we're looking at is at different exposure times will give you the same absorption rate in your blood, right? So it's basically it's that cumulative effect. So what we're saying is you can get low level CO poisoning. You can have a small amount of CO, 75, 50 parts per million of CO in your air, in your air at your house, and have a CO alarm never ever go off, and you're getting this buildup of CO in your blood over time because your exposure in minutes. This only goes from 0 minutes to 240, so at 2 hours there, right? Or 4 hours, excuse me. So we're not talking about tremendous amounts of time here. What if you're in your? I sleep more than 4 hours at my house. I'd hope everybody else does. So I mean, we're talking about 10 hours. You're home all weekend. A small amount of CO could build up in your blood over time, and you could be getting all kinds of symptoms: the headaches, nausea, drowsiness, vomiting. You think you got the flu, and you got CO in your blood. All right, so combustion safety test action levels. CO measurements for undiluted flue gases at steady state, okay? And here's right out of BPI standards. Somebody was just asking what those standards are. Undiluted is the same thing as CO air free, right? Because we're talking about dilution by oxygen. So if we say, okay, I'm gonna make that apples to apples, I'm gonna say all the flue gases are undiluted. Well, here's what it is, right? So 0 to 25 ppm, and it passes the spillage and draft test. And we're gonna talk about that in a few minutes. You can proceed with your work, right? 26 to 100, and it passes the spillage test. We're gonna recommend that CO problem be fixed. 26 to 100 and it fails, at worst case only, well, we got to recommend a service call for the appliance. We're going to get a heating contractor out there and do repairs to the home to correct the problem. 100 to 400 ppm and fails under natural conditions, stop work. This is a dangerous appliance at this point because it could definitely put enough CO into the house to cause some problems. Greater than 400 ppm and passes, stop work, and greater than 400 ppm and passes, fails under any condition. Now, we're talking about stop work. What we're talking about is stop weatherizing the home. Don't seal any windows, don't caulk any doors, don't do anything. I can't proceed with any weatherization in the home till that furnace is fixed. You've got to realize the ANSI standard is 400 ppm. That's the maximum amount allowable in the stack, okay? We know as an industry we can get well below 100 ppm under normal conditions. There's absolutely no reason a furnace has to produce over 100 ppm of CO. Are there furnaces that do? Absolutely. Are there sometimes furnaces we can't repair? Absolutely. I've run across them. There's sometimes problems that it produces large amounts of CO because of a lousy burner design. And there's just nothing you can do about that except recommend changing out the appliance. Most modern appliances you're going to be running, you know, well below 100 ppm, and they're going to be typically, you know, somewhere around that 20 to 30 ppm of CO. Actually, excuse me, 20 to 30 ppm maximum, and you know, I see a lot of appliances running no CO at all. Now, there's other sources of CO, and you really got to watch this because I've been caught on this myself. CO can go right through the combustion process. So if you have CO in the house, you know, you went outside, you zeroed your meter outside like you're supposed to, you come inside, you don't test ambient CO in the home, and you know, you're watching your furnace run, and you had 10 ppm of CO come in, it can come right out the other end of the burner, and I've actually seen it happen. We had a customer one time, we're testing the furnace, and all of a sudden the CO level in the burner starts to rise, and we're looking for problems with combustion air. You know, we're thinking, well, we must be starving the appliance for combustion air, something else is going on. We're checking the fuel regulator to see if we're overfeeding for gas, can't find anything. Well, here the customer started their car in their garage, and CO was coming right through the, you know, on the sill plate from the garage into the basement, getting picked up in the combustion air, going right through the combustion process and raising the stack level CO. And I'm sitting there thinking it's a furnace problem, and it was an auto problem. So, you know, that can happen. Some possible sources can be fuel burning furnaces and the hot water heaters. Believe it or not, those aren't the #1 causes of CO in a home. It's actually auto emissions. We can also have it, you know, from our kitchen range or oven, our fireplaces, tobacco smoke, fuel burning space heaters, you know, fuel burning boilers. You got to remember, if these appliances are burning right, like your oven and your range, you know, it's burning, it's venting right in your kitchen. I mean, the flue gases are going right in your kitchen. If it's burning right, it's giving you carbon dioxide, water vapor, and heat. It's really not producing as much CO. And if it does produce a little bit of CO, and there's enough dilution air in a typical home that it's not going to raise the CO level in the home that's even measurable. But if that appliance isn't burning right, it can be a very significant source of CO in the home. So these are things we got to watch. Tobacco smoke. I've seen people doing incense and candles causing CO, elevated CO in a home. Fuel burning space heaters and fuel burning boilers. When we sample for CO testing, we're actually, you've got to get a good process together, because you can't just test the appliance. We actually want to sample from entry to exit. In other words, from the time you enter that home to the time you exit that home, you should be sampling for CO. Because even the testing we're doing could be exposing us to CO. So we have to be extremely careful when we're doing this kind of stuff. We have to sample around all unvented appliances. Okay, and I know BPI is telling you guys to pull all those appliances out, not even allow people to use them. But you know, a lot of the rest of the gas industry, people are still using unvented gas logs. People are using unvented space heaters. In the right applications, there's nothing wrong with those type of appliances. They aren't used as a main source of heat. They're used for ambiance, or they're used for, you know, temporary heat sources. There's not a lot of danger with those types of appliances if they're serviced properly, if they're set up properly, installed properly. And the problem is, you know, Joe homeowner goes out and buys one, puts it in his bathroom, and it's exposed to things like hairspray, and it's exposed to you know, a lack of combustion air because it's in a little tiny room, and the bathroom exhaust fans competing for combustion air. You know, those are where we find problems. Those appliances absolutely do need removed. But you know, a properly installed ventless appliance, if it's working the way it's engineered to work, is really not that dangerous at all. But sample where you suspect, anywhere you might suspect CO. The national standards for CO exposure, less than 9 parts per million. That's the ASHRAE 6289 standard, and that's indoor versus outdoor air. If you live in New York City, you're going to have CO in your air outside. You walk outside, you're getting exposed to CO. You know, back in the day, they used to say you need to go to the country and get some fresh air. That's because your air is lousy in New York, and you need some fresh air because your body's getting poisoned by CO, which is a cumulative poison. You got this stuff building up your blood. You get away, you get some fresh air, you will feel better. So that's what, you know, we're talking about over ambient. You can't fix what's in your air. You can't get that out of there. If that's what's outside, that's what's outside. It's also going to be the same as inside. What we're concerned about is that, is there a difference between inside and outside? If I walk in the house, you know, if I zero my meter outside, it's basically called nulling your meter. And nulling your meter means that you're telling it that basically with reference to outdoors. So I calibrate it outside, and it's going to zero out. It's going to say, I'm ignoring that 9 parts per million that's outside, because it's not an absolute measurement. It's a relative measurement. You know, relative, and we're looking at relative to outdoors, what's the CO indoors? So if I zero my meter outside and I go inside and I'm reading 2 parts per million, well, I have something producing CO in the home, right? And that's when we want to start to do an investigation. Now, if we're talking worker exposure limit, you can be exposed to less than 50 parts per million for 1 hour over an 8-hour period, okay? The EPA recommends less than 9 ppm in the living area over 24-hour exposure. And then the ANSI standard, ANSI Z21.1, is less than 400 ppm air-free in the flue gas or undiluted CO. Okay, that's the other, we'll do that. So here's some national standards for CO. The ambient air action levels for BPI is 1 to 9 parts per million is normal, and there's no action required. I've been doing this enough years. If I see anything above 0, I want to know what the heck's causing it, because to me, 0 CO is normal. There shouldn't be any CO in the house. I have a stove, a gas stove in my house, and it'll kick my CO level up to 1 or 2 parts per million on Thanksgiving Day when my wife's running that thing, you know, 8-9 hours a day. But, you know, if she kicks the stove on normally, it doesn't ever cause my CO to rise. When it does, I know something's out of whack, and I've had to adjust my stove before the bottom pan got knocked out of place, and it was causing some small amounts of CO in the house. But no CO is normal, okay? If we're producing CO in a home, the problem is how high is it going to go? Because, you know, you might be there on a 40-degree day. Well, the furnace is running, you know, a couple hours a day. What's it doing on a 0-degree day when it's running 24 hours a day? And it may not be the furnace that's causing the problem. It may be the car. You know, a 0-degree day, your wife goes out and pushes the auto start in the garage and lets the car warm up in the garage. She's got the garage door open, but maybe the wind's blowing in the garage, pressurizing the inside of your garage and moving that CO right into your house. You know, so any CO in the house we really should investigate. 10 to 35 parts per million, they say, is marginal. Advise and ventilate the home. 36 to 99 is excessive. You need to check, mitigate, and ventilate. And I always tell people the way I look at it is you know, 2 things I want to tell people are vacate and ventilate. Get out of the house. If the CO levels are 36 to 99 parts per million or even higher than that, you need to get out of there, because you're putting yourself in a dangerous situation. You could be overcome by it, and you may not even have time to react to it. You can walk into, I've seen CO levels in furnace stacks over 19,000 parts per million. If that was venting in the space, you may not have a chance to even react to it before you get overcome by CO. You know, 100 to 200 parts per million in ambient air, it's extremely dangerous. You should call 911. You know, you should get the occupants checked, because they probably are going to have some CO poisoning. CO home alarms. You know, everybody goes, oh, I'll just buy a CO alarm, I'll be safe. Well, in Chicago, back in the day when they first came out with these things, they had much lower alarm levels, and they were going off like crazy because people were having all kinds of CO problems in their homes, and the fire department's going nuts. So instead of fixing the CO problems, in their infinite wisdom, they decided, let's change the levels on the alarms. So you could actually have between 65 and 75 ppm in your house for 60 to 240 minutes, and that alarm is not allowed to go off, right? So 75 ppm, let's say your furnace kicks on, runs for 15, 20 minutes. It's kicking out 75 parts per million, right? Or even 100, if you look there, 100 to 155 ppm. 15 minutes is running. Shuts off, goes back down. CO goes back down. Kicks back on, CO goes back up. Kicks back off, CO goes back down. You're being exposed to CO in your home over and over and over again. That alarm's not allowed to go off. right? If you have 27 to 33 parts per million exposed for 30 days, the alarm must not sound. So, we're looking at 9 parts per million as a BPI standard, yet your standard CO alarm is not even going to be beeping, indicating there's anything wrong if that CO level is running 27 to 33 parts per million. And at 65 to 75 parts per million, it cannot alarm if it's exposed for 60 minutes. So, these things are, to me, a little bit disturbing, but that's the reality of the world we live in today. They do make low-level alarms, and we sell them. TruTech Tools sells them. Other places sell them too. And believe it or not, they're not UL listed, because what we're looking at is the UL standard. The UL standard says you can't let those alarms alarm. So these alarms are low-level alarms, and they'll go off as low as 7 ppm. And you typically, if you have somebody that's sick in the house, an infant in the house, elderly person in the house, somebody that's housebound, right? Kids, these are people that aren't going to be as tolerant to low levels of CO in the house than a healthy adult would. Got to remember, all the CO testing we've done has been done on military people. I think they're probably in a little better shape than most of us are. They're going to have better lung capacity. They're going to have they're working out. They're in good shape. Most of us aren't in good shape, so most of us aren't going to be able to survive as well in higher CO as somebody like that would. But they're recommended, we recommend anybody that weatherizes the home, because now we've changed the dynamics of the structure, and we want to make sure that if there's CO in a home, we want to make sure that we're aware of it, because the only way we can fix it is if we know. So why test a unadjustable appliance, right? This is the question I got from the contractor. I said it disturbed me a little earlier. Well, because that appliance is installed in a dynamic environment, right? You put your furnace in the basement, you hook the thing up, it's affected by pressures in the combustion air zone, right? You kick on the dryer, that could affect the furnace. It's affected by the fuel pressure. It's affected by changes in the blower speed. A blower speed goes from high to low. You have a variable speed blower in the house. You have a modulating furnace. The blower speed's ramping up. You got some duct leakage maybe. All of a sudden it gets to the point where the blower overcomes the combustion air and it's back spilling into the house. Could be affected by duct sealing. Maybe you're sealing up the supply ducts. All of a sudden the air that the furnace is using for combustion, you just cut it off because you sealed the supply duct up, and the hole that was in the supply duct that was giving you the right amount of air in the room. It's affected by the environment it's installed in, right? It's things in the combustion air zone, by the installation itself. And we got to test it for the safety of yourself and the consumer. So why performance test? Well, ensure reliability, ensure appliance safety, minimize the liability. We're going to improve preventive maintenance and fuel savings, improve our professional image. We're going to demonstrate the manufacturers we know what we're doing. We're going to increase our company's profits because we're going to get quicker service calls. We're going to find work. Combustion, dilution, ventilation, air problems are something that we can solve in our industry and actually provide solutions for, and solutions that we can bill for. And we're gonna make sure that we meet standards of our national installation verification programs. And we want to avoid nuisance lockouts like this one, where the burners went out and the water pipes broke in the garage. That is a Porsche, an Explorer, and a Volkswagen underneath the ice. It's a good thing they have AAA. And everybody does such great routine maintenance. I went out on a job in a nursing home. This is a nursing home in Coshocton, Ohio I went to, and the boiler's plugging away in the basement, and they asked me to come and they're having problems with the boiler tripping on the pressure switch. So what's the mechanic do? Pressure switch is tripping? Let's just adjust the pressure switch till it keeps the boiler on. I get there and look, and here's the combustion air intake. When they closed the doors to the boiler room, the boiler was not getting enough combustion air because the intake air is so filthy. And a technician was trying to keep the boiler on, adjusted the safety right out of the boiler. So these things happen. Because things like this never happen. This is a chimney liner, right? Slides down the chimney to downsize the stack so that we don't get issues with condensation. Well, obviously these issues weren't overcome because, again, I told you flue gases contain acids. Well, you can see what that acid does to aluminum. It ate it away, and the chimney liner literally rotted inside the chimney, and good wind came by and tore this thing right off, and it's damage from condensation. And this was an uninsulated liner. I'll bet you about 1% of our industry actually pulls an insulation sleeve around the chimney liner when they install them. And if that chimney liner is contacting the brick on the chimney, it's aluminum and conductive, and it'll cause problems with condensation. This is a house I did in Akron, and had a neurosurgery for one of the main hospitals here. And get in the house, and if it looks good on the inside, outside, it must look good on the inside too, right? Why combustion test? Well, do you think maybe this furnace was having some combustion air problems? Every vent in the house is covered, a supply vent, and she's having problems with depressurization of the combustion air zone because we're not getting the air moving around the house the way that we should. Furnace is overheating, heat exchanger problems, and these are things that you run across periodically. All right, safety testing. So how are we going to do this? Well, most important thing, zero the analyzer in a non-contaminated environment. Typically that means you're getting out into fresh air. We're gonna zero that thing in fresh air. It's going to go through a countdown, and then we're going to be able to do our testing. So we're going to zero it, test the air. We're going to test in the flue. We want to make sure we get an undiluted sample. And this is particularly in larger flues. We need to find the hot spot or the core sample in the flue. The hottest spot in the flue is where we want to measure. Again, these are air-free or undiluted samples. If we're talking ambient CO, we want to also be near combustion sources. And we always want to test unvented combustion appliances. Air-free measurements, we talked about that. CO air-free is simply equals the CO times 20.9% oxygen divided by 20.9% minus the O2 left in the flue gases. It's just a formula to correct for the excess air. But here's what you need to know. In order to get undiluted CO readings, you have to use a combustion analyzer. You cannot use a raw CO sensor, and they sell them. They sell analyzers for $800 or $600 that measure CO, and they aren't a combustion analyzer, but all they make is a raw CO measurement. And that raw CO measurement is no good for meeting any of the standards. They sell them because people buy them, and they do exactly what they say they'll do, but people don't know what the standard is or how to meet it. So I'm telling you right now, if you're using that type of appliance, you can't do the testing that's outlined in the standards, and you need to get a combustion analyzer. All right, some notes on NOx. NOx, or oxides of nitrogen, are created by nitrogen in the flame, right? But NOx, oxides of nitrogen, actually fool the CO sensor. And almost all combustion processes have NOx, right? You're burning it, you get oxides of nitrogen in there, especially on newer burners, because these newer burners are burning a little bit hotter. It's pretty common to see NOx. And they fool that from a factor of 0.4 to 0.5. So what that's saying is if you had 100 ppm of NO in the flue gas, that's going to register as 40 to 50 ppm of false CO. Okay, so this is of particular importance to people doing BPI, energy auditing, energy testing. You need to make sure that you have a NOx filter in your measurement. And you never ever want to make a measurement without a NOx filter. Now, all the testo meters, 327, 330, 325M, they all come standard with a NOx filter. And I have the CL cell pulled apart in that picture to show you the filter. And that filter will last the life of the CO cell unless you're getting something that's got a ridiculous amount of NOx in it. And if you throw it on test gas, and we use, like at TruTech when we're doing combustion tests, we actually order our test gas that's a combination of CO and NOx, so we can test the NOx filter. And it's available as an accessory for all back rack products. So if you own a back rack meter and it's not the Insight, you probably need to order a NOx filter for it. And it's like $45. You just throw it in line, and it strips that NOx out, and it gives you a true CO reading. And we need that because the reading always does matter. We don't, we have a responsibility to know whether we're measuring CO or CO and NOx. Here's a 327 I took a picture of that had a NOx filter in it versus a Bacharach that had no NOx filter on it. Now again, this is available as an accessory. You can see the Tesla was reading 6 ppm. The Bacharach without the NOx filter is reading 27 ppm, right? And one thing we got a safe appliance, the other one we got a call to action as far as the BPI standard is concerned, right? So, you know, if you don't have the sensor on there, you can be chasing around a problem that really doesn't exist because it's cross interference from the NOx that's causing the high CO reading. All right, so let's walk through the steps to perform a complete combustion analysis. First of all, you should always carry a single gas CO monitor because there's a high probability at some point in your career this thing will save your life because you don't know when you're walking in a home, a business, a boiler room, anything else with CO. I particularly like, we sell the Testo and the Sensit P100. I particularly like the Sensit just because it's auditory. It beeps, it vibrates, and it's got a flashing light on it, and as well as a display. The Testo is a great meter, and it's temperature compensated, which is really nice because you can put it in a warm air stream, and it's not going to give it a false high CO reading. We sell probably about half and half of each, but they're fairly inexpensive. The Sensit P100 is an always-on meter, so once you turn it on, it never shuts off. You know, if it clips to your belt and it's on 24/7, 365 till the cell expires, and typically lasts about 2 years, and you have to replace it. Same thing with the Testo; they have about 2 to 3 year lifespan. All right, so just you know, we go out and do testing. We do some live training and stuff, and 4/18/2009, you know, we're at the Hampton Inn, Richfield, Ohio, HVAC TruTech training symposium, and you know, we're sitting around eating breakfast, and Gary Reacher is got a CO alarm on his belt, and this thing starts beeping. And at first, we're sitting there thinking, "What the heck's wrong with that thing?" You know, I mean, here we are. We're all. I mean, I teach this for a living, and I'm sitting there eating breakfast, and the CO alarm goes off. It's 35 ppm in the lobby, and 56 ppm in the hotel hallways. We're walking down the hallway, the CO level's going up, and it's climbing as we're going towards the boiler room. And at this point, you know, all of a sudden, I go, holy cow, something's really wrong here. At this point, you know, it's, well, what do you do? Well, I got 24 guys attending this class, and, you know, we're all HVAC contractors, and everybody wants to go out and figure out what the heck's wrong. Well, that's exactly the wrong thing to do. What we ended up doing was we called the fire department. Because at 35 parts per million, this is, you know, right in Richfield, this is the actual picture of the truck rolling up here, and the fire department starts donning their SCBA, self-contained breathing apparatuses, because above 35 parts per million, these guys aren't taking any chances. They want to make sure they're not going to get sick or killed, right? So everybody's putting on self-contained breathing apparatuses. They go into the hotel pool room, and this is actually a boiler in there that's pouring CO into the place. Throw a fan in, and they start ventilating the CO out of the space. They got to get the CO out of the building. They eventually get the CO down far enough, and they go in and secure the boiler. You can see they shut the gas off there. And they got the space down. They tested the space, got it down below 9 parts per million, and then we went in to do some testing and actually see what was wrong. And what we found out is, in this boiler room, somebody had disconnected the makeup air, and they put on a you know, a damper. They closed the damper. Well, that damper seals about as well as nothing. And they had disconnected the makeup air because obviously who the heck would want to bring in fresh air into a building, right? That doesn't make sense. So somebody in their infinite wisdom disconnected it. Then, you know, because the combustion air inlet was right over the pool pump, and at one point it had frozen the pool pump lines, it's obvious that you need to stuff that with rags, right, so it doesn't freeze. So that's what their in-house mechanic did. So we got an air handler depressurizing the thing. We got a rag stuffed with our intake combustion air pipe stuffed with rags. And then to top it all off, you look up at the air handler, and the filter rack's open, right, wide open. Now, I just had a contractor out for service. And, you know, the moral of the story is if you don't take time to look, somebody else will, because, you know, here we all are, 25 guys looking at this thing, and we're looking at mechanical, whatever, ink, right? And this guy may as well just put up a sticker up there when they left this door open that says, "I love lawyers," because here's the hotel saying we just had somebody out for service and they didn't find any of this stuff. They're all upset. The guy changed the filters, leaves the filter door open, doesn't connect the makeup air, doesn't check the makeup air for the boiler. So it's like, these are, you want to leave yourself a liability, don't learn how to test properly. And this is a real story. I mean, you can see right here is a copy of the letter. We apologize for the inconvenience this morning due to gas leakage in the pool room. The carbon monoxide gas leakage in the pool room, which is different from the main motel. We had a detector. The fire department was here within 15 minutes. They checked every floor, and everybody at the symposium ended up with a bottle of champagne in their room that night and a copy of this letter. So I mean, this stuff does happen, and here we are thinking, we're in a motel room. What could happen here? We're having a workshop, and it was a very good lesson for us, and a good lesson for the guys that were there, because in reality, you don't want to walk in. If nobody would have had a personal CO alarm, we could have walked right into that room, and who knows what the level was in that room. I really don't want to know. What I want to know is that nobody went in there, nobody got hurt, and that's the same thing you should do if you're out doing an inspection on the home. All right, the key thing for HVAC contractors, if there's any of you guys in here, remember the building is a system. All right, in the building science community, I know BPI is ruffling a lot of feathers in the HVAC industry, saying, all of a sudden guys are going out and testing your installations, and installations are failing, and guys are upset because who's this guy to come out and tell me? Well, we got a new set of standards, and people are testing equipment differently than you have, and they're finding out that it doesn't always operate the way that you anticipated it would, and there's problems that need to be fixed, and so we got to relook at the way that we're doing things. All right, so now that we got past my intro warning here, let's talk about what step one is. Step one, when you walk in, you're going to do a combustion test. Okay, you got to realize a combustion analyzer like the Testo 330, Testo 327, I think even the back rack will do this, an ambient CO test. Prior to entering the home or the boiler room, right, we're going to zero the meter outside. Okay, so you're going to stand out by your car with your car off, and you're going to start the meter up, and you're going to let it zero in the ambient air, and it's going to null out any ambient CO in the air, and we're going to have that pump runner. We're going to walk in the house, and we're going to push start, and we're going to check that ambient CO as we walk through the home, and we're going to test it all the way down to the boiler's room. And the reason we're going to, even though you got the personal CO meter strapped to your belt or strapped to your pocket, we're going to test this because the analyzer is going to allow us to record it. So if we have the ability to print it, which I hope you guys, if you don't own a printer, that you consider purchasing one, because the printer is a very nice way to leave documentation of what you tested on the job. You print a copy for you, print a copy for your customer, staple it to your work order. It gives you the date, the time, the serial number of the analyzer, and you're going to leave a combustion test along with the ambient CO readings that you read, so you can show that while you were doing your testing, while you were there, it was safe, right? But if the CO levels exceed 35 parts per million, stop testing, right? And we want to get, obviously, if it's above 100, even above 35, vacate the home, ventilate the house, leave the doors open as you're leaving the house. And we got to, I would secure the fuel supply. If we're talking gas, shut the gas off to the house, and then you're going to have to go, wait till that's cleared out and go in and test. If you don't own the right equipment, you have to call the fire department to come out and ventilate the house. That's what you got to do. But typically, you're not going to run across that kind of thing. But if you do, you got to vacate, then ventilate. Zero the analyzer outside if required. Almost all of them do. Now, the personal alarms like the Sensit P100 and the Testo 317-3, those are absolute sensors, so they do not require zeroing in fresh air. They're always on. They're making an absolute reading. They're not a relative sensor like a combustion analyzer in. We want to test around all levels of the home. We want to test around the heating appliance and the hot water tank at all times during testing. If the ambient CO levels exceed 35 parts per million any time during the testing, turn off the appliance and immediately make repair recommendations, okay? Because we're talking about, somehow you're getting CO into the space. above 35 parts per million, not safe. So shut the appliance down. As a contractor, I don't care whether you're BPI or ResNet or HVAC contractor, you have the right to shut off the appliance and tag it that it's not safe. Okay? You can shut it off, put a red tag on it, and say do not operate, unsafe to operate. You have that right as a contractor to do that. I don't care what kind of a contractor you are, you have that right. Now the homeowner has the right to tear your tag off and relight their appliance and restart it. Well, hopefully they don't do that. But you know, you sign off, and typically when you're talking a tag for that, you're going to want a 3-part NCR tag. You're going to leave, you know, 1 copy with the homeowner. You're going to leave 1 copy with you, and you should give a copy to the jurisdiction having authority, which is typically like your utility. You have a gas appliance making CO, and it's in excess of what it should be. You valve that thing off. You keep a copy of it. You have the homeowner sign off on it that they understand that it's dangerous, and you can give a copy to the utility. Somebody's got to fix that appliance before it's turned back on again. Now, you could walk out the door and the homeowner could tear that tag off. Nothing you can do about it. They could relight their appliance. Nothing you can do about it. But you have to be diligent in doing that. Otherwise, that person dies. You're called negligent, and you don't want to be negligent in a poisoning death. All right, how to interpret the measurements? Well, we're going to test the ambient CO from the front door to the combustion appliance. We're going to test under different conditions, right? It's called worst case. We're going to set up. We're going to do it with the fans and the appliances. We're going to test the room air and the flue gas. We're going to print that information out when we're done. So now that we've tested the ambient CO, and again, we're going to carry an ambient CO meter with us so we make sure we're safe all the time. Now is when we're going to set up worst case depressurization testing. And this is required by BPI. And if you're an HVAC contractor, this is, I believe, Section D in the appendix of the National Fuel and Gas Code. And believe it or not, because it's an appendix of the code, it's recommended by it, but it's not required. But it's still a standard. So you're required to set up worst case conditions. We want to monitor the CO during worst case conditions and the stability of the combustion process during this test. And obviously we want to watch for spillage and rollout. The question is, when we're doing worst case testing, is will you create enough competition to backdraft the water heater or the furnace? And there are limits for worst case depressurization, depending on the type of the appliance. And you can reference this slide. Again, it's courtesy of the BPI standards. But if we have an orphan natural draft water heater, that means the water heater is all by itself. There's no furnace in with it. It's got a limit of 2 pascals in the combustion air zone, negative pressure with reference to outdoors. A natural draft boiler, 3 pascals. A natural draft boiler with a vent damper, commonly vented with a water heater, 5 pascals. So you can see that different scenarios have different limits of depressurization that are acceptable. We're going to set up worst case, and we're going to test for spillage. Okay, and spillage means, are the flue gases going up the chimney, or are they going into the space? And you want to test about a ½ inch down and a ½ inch out from the outer edge of the hood. And we use typically a paraffin wax type candle to do that. They're like, I don't know, like $35 for a pack of them and a bunch of wicks. You can light it, and you snuff it out, and it smokes. And basically what we're trying to make sure of is that with that ½ inch down and ½ inch out, that there's enough dilution air entering that hood, and the flue gases are going up, and we're safe. So after a minute operation of the flue gases being pulled up the hood, and you got to give it enough time, you know, for the chimney to warm up and that thing to start venting properly. So we've done our ambient CO test, right? We've done our let's just back up here a little bit. My brain just took a dive here. Step 2, we set up our worst case conditions, right? We've tested our spillage, and now we're going to draft test. Our draft test removes the flue gases, and draft controls the airflow through the heat exchanger. Now, I have that starred there because what I want you to realize is draft physically separates the appliance from the chimney. Okay, so this is really important on atmospheric draft appliances that you understand this. What pulls in the primary air you know, and we're talking about, let me grab a marker here, felt tip pen. We'll see if I can draw with this thing. I never tried it before. Primary air is air that's entering the burner right here, okay? And primary air is entrained by the gas stream fired into the burner. So as a gas shoots into the burner, it pulls in primary air through the venturi. Secondary air is air that goes around the burner up into the combustion chamber. And secondary air assures complete combustion, right? And because the flue gases are naturally buoyant and hot, that warm air rises, right? That warm air rises, it's going to pull in the secondary air right behind it. So the primary air is entrained by the burner and the venturi. The secondary air is entrained by the flue gases being naturally buoyant, flowing up to the heat exchanger. Now the heat exchanger, if you look like right here, it's physically separated from the draft. So this area here, outside here, this is our normal dilution air mixture. That is a neutral pressure zone, not positive, not negative. Here in the chimney, it's a negative pressure zone, right? It's negative pressure. And so we're going to pull from the neutral pressure zone into the negative. And in here, in the heat exchanger, in the top of this is actually positive pressure, because you're pulling in that hot flue gas and that burner's burning, you're forcing gases in there, you're building a positive pressure, and the pressure should flow from positive to negative, right, and go right up the chimney, okay? But the appliance, the draft, is engineered so it doesn't suck the flue gases out of the chimney. It dilutes it doesn't suck them out. They naturally flow out, and the chimney is the area of lowest pressure, and it flows up and out the chimney. And in the process also it pulls in enough dilution air that it keeps it from condensing. All right, so the draft hood simply separates the appliance from the draft because the draft pressure is below the house pressure, and the flue gases and dilution air flow from high to low. And spillage occurs when the draft is overcome or simply not enough. Right, if our chimney's not drafting properly, it's going to spill into the space. Now I'm going to go back to the slide for just a minute. Here's what we're looking at. So let's say that the chimney doesn't draft properly. Let me see if I can clear this off here. Let's see here. Let's see here. Yep, we'll go back. I don't know if I clear that off or not. If the flue gases, sorry. Let me get my pen back. All right, here's why the draft hood is developed, because everybody goes, why in the heck would they have this crazy idea of putting a draft hood on? That really doesn't make any sense. But have you ever seen the movie Backdraft, right? The whole is a 1980s movie. Firefighters are in there. The fire's burning inside a closed room, right? And they open up the doors, and the fire would explode out the front, right? And the whole thing of the movie was fire looks for air. Well, that is extremely true, right? Fire always wants to find oxygen. So if we didn't have the draft hood that we have on here, find my felt tip here, yeah, there it is. All right, what we're looking at doing is we can either allow those flue gases to spill in the space, right, which is what they do. They go out the draft hood opening if the chimney was blocked. So we got blockage in here, we got a bird in here, whatever. This is all blocked off, right? No draft in the appliance. Well, the flue gases, which are naturally buoyant, are just going to spill out the front of the heat exchanger. They're going to spill out the front. And this is much safer than the flame trying to come out here and look for oxygen. Because if the flame comes outside of the burner compartment, it's going to cause a fire. So the draft hood was engineered to keep furnaces from catching on fire. Because if the combustion is correct, carbon dioxide, water vapor, heat, that's all you're going to get in the house, right? Now that water vapor is going to cause humidity problems. It's going to cause moisture raining off the windows. You walk in the house, you see moisture ringing off the windows, you probably have flue gas spillage in there. But as long as that appliance is burning properly, all you're going to get is carbon dioxide, water vapor, and heat. You're not going to get CO. You're not going to kill anybody. Now the issue becomes is if enough of that flue gas keeps recirculating in the house, eventually you're going to displace the oxygen and you're going to start to make CO. So we don't want this to happen for long periods of time. But if you had a bird fly down your chimney in the middle of the night and your flue gas spilled overnight, odds are you're going to be a heck of a lot safer with a little flue gas spilling in your house than you are with your house catching on fire. And that's the way the appliances were engineered that way. So it's, the draft hood is engineered for safety. And today, we don't have draft hoods, so we have rollout switches. So now if the flame comes out backwards, it impinges on a rollout switch and shuts the burner off. All right, so we hit the slide here, and we're going to draft. So how are we going to draft test? Well, you need to be at least 2 times the diameter of the flue from the draft hood. So you can see up here with this, right here is where I'm testing in the flue pipe, right? We want to be at least 2 times the diameter away. We really ideally want to be away from elbows and transitions in the flue pipe because they can cause some eddy currents in there. But under typical conditions, the flow is so low, they don't have a huge impact on it. But you want to hold that test probe perpendicular to the stack when testing. And after that appliance is run for about a minute, we want to make sure the flue gas is being pulled up the hood and we have correct draft. As the chimney warms up, the draft is going to increase, or could increase. It should increase because you're going to flow those flue gases up faster and faster because we have a higher differential temperature between the outdoor air temp and the flue gas temp. So what's the acceptable draft range? Well, BPI has a standard for that. There's actually a formula for that, right? And it's telling us the minimum amount of draft we're allowed to have is 2.5 pascals, and that's minimum draft at greater than 10, or my brain's dying here, greater than 10 degrees, or less than 10 degrees, excuse me, it's 2.5 pascals. At greater than 90 degrees, it's 0.5 pascal. And anywhere in between that, there's a formula. The temperature outside divided by 40 minus 2.75. So I ran some quickly just so we could see them here, but basically, at 10 degrees or less, 2.5 pascals. 30 degrees, 2 pascals. 50 degrees, 1.5 pascals. 70 degrees, 1 pascal, right? 90, 0.5 pascal. As you guys are doing weatherization, an HVAC guy probably isn't going out and testing draft on a furnace on a 90-degree day. He's probably working on the air conditioning. But if you're weatherizing a home, you got to have 0.5 pascal negative pressure, or you don't have enough draft on there. So you need a precision draft meter to do that. Excessive draft, though, you don't have too much draft because it's going to lower the appliance efficiency. You can actually start to pull the flue gases out of the appliance, and not enough draft is going to compromise your safety. When you get copies of the slides, you can print this out if you want. We ran the whole thing, less than 10, 12, 14, 16, 18, all the way up to 90, what the minimum draft is in pascals. So, we set up worst case. We gone through all this testing, and we test draft. Well, if there's no draft under worst case, then we got to return it to natural conditions. If there's still no draft, you got to stop here until the combustion air zone problems are fixed, right? We're testing under the worst case. And again, if there's no draft under the worst case, well, then let's turn it back to where it was. And if there's still no draft, you got a serious problem. You got flue gases aren't going up the chimney. So what causes typical failures of too little draft? Well, too much competition for air, right? Not enough makeup air in the house. Not enough air available. Too small of a space the appliance is put in. Blockage in the chimney, right? This one here, you can see this chicken wire they put in this chimney right here. It's blocking off the outlet of the chimney. Poor system design, duct leakage, negative pressures in it overcoming the draft. Too much draft can be caused by an oversized chimney. And I just like this picture here. It's actually a building behind that house, but I thought, boy, it does look like an oversized chimney. Excessive stack temperatures or power vented equipment that's not set up right. So now, step 4, if our draft passes under worst case, we're going to test under the worst case conditions. We're going to run this through a complete cycle. So we're going to start the furnace. On natural draft appliances, on gas appliances, natural gas, not natural draft, natural gas appliances, you do not want to put your analyzer in the stack when the burner lights, because all of them will make a spike of CO when it initially starts. And all you're going to do is you're going to see it spikes for 1,000 ppm for 2 seconds. Yay, that was exciting to see. You can't fix that. There's not much you can do about that. It could be indicative of a rough light off. It could be a burner issue, but for the most part, you got an igniter on one side of the burner. You got a flame rod on the other side. It ignites on one end. It's got to work its way across. There's going to be some unburned gas that lights a split second behind the first burner lighting. All right? that spike CO reading is pretty much meaningless to 99% of the guys in the industry. That spike CO reading is just putting unnecessary wear and tear on your meter. So start the furnace up, let it run for a minute or two, let it clear out that initial spike reading of CO, then start your test, okay? You want to test it through a full combustion cycle. Once you got it in the stack, you're going to leave it in the stack. We're going to let the blower start up. We're going to let the furnace warm up. We're going to let the thing come up to operating temperature. We're going to make sure that, that everything's operating consistently and safely. Now there's an issue in this picture right here. This young man I have took a picture of him doing a combustion test. And the issue is right here is the, you know, he walked up to the furnace. He started to work on it. He took off the door. Well, that's a sealed combustion appliance. And as soon as the door's off, it's no longer sealed combustion. So now he's pulling air from the space, from the room he's working in, instead of air through the inlet air pipe, right? Right here's the inlet air pipe, and it's going down. It goes down into the furnace cabinet right here. And this is obviously the exhaust going out here up this way. And here this young guy is. He's got the door off the furnace. He's doing a CO test in the stack. The whole dynamics of combustion have just changed. If he would have put this door back on here, what he would have found out is that I had a rag stuffed in this pipe and that the furnace wasn't getting any combustion air and it's producing massive amounts of CO. But with the door off, he completely missed the problem. And that was the exercise we were teaching. All right, heat exchangers. I don't care whether you're BPI or a heating contractor, you should do a visual examination of the heat exchangers. I want to talk a little bit about testing. All these are failures. This is rotted out due to condensation in the bottom of the tubes. This is a split right here in the bottom. You can see where it cracked, a large crack up the side, split in the back, typically from overfiring the appliance. So there is the latest testing that was done for heat exchangers, I believe, is the 1989 standard, RSDS publication 630, 92, 96, 86. So it's 1986 is the most current standard. They recommended a 3-part test, and it's a flame disruption test, a visual examination, and a chemical test. And we're going to talk about all 3 of these. And it's really, you know, as an HVAC contractor, what you'd be watching, first of all, is you'd start the burner up, and you'd watch the flames. And we're seeing if the flames get affected when the blower kicks on. We're doing a visual examination with some scopes and meters, and we're doing a chemical test. I'm going to walk you through all 3 on these. Now realize heat exchangers are not hermetically sealed. Hermetically sealed means totally sealed, right? They all leak a little bit because, you know, they're not, you know, they're welded and they're crimped shut, but, you know, they're not gonna stop every bit of gas from getting out of that appliance. Most of them are really good, but the manufacturer states that they could have a standard, manufacturing standard for heat exchangers is they're allowed to have the equivalent of 1/8 of an inch hole leakage. The problem with this is it's impossible to do in the field. I can't tell you if the total leakage of a heat exchanger is 1/8 of an inch. So the industry standard is simply if you find a failure in a heat exchanger, I mean, I don't care if it's a crack you can't even fit a credit card through, it's a failed heat exchanger. You know, if you find a crack in the heat exchanger, it's a crack. The heat exchanger is failed. The appliance should be replaced. There is no repair of a heat exchanger. You can replace a heat exchanger. Most of the time it's not economical to do it, but any failure is a failure. All right, so let's talk about the flame disruption test. And we talked about this one slide a little earlier, but you can see a normal flame there on the right, and we have the flame here on the left affected by the blower. So that flame looked straight up and down, but when the blower kicked on, that flame started moving to the left, or to the right, excuse me, and when it hit the side of the heat exchanger, it starts making CO. Shut the blower off, the flame will go back up to straight again. It's a failed heat exchanger, right? So that one's the one we have to be concerned about. Somebody was going to ask me here, I'm sure, right here by the thermocouple, and you know, what's this on the side here? That's a pilot that you're seeing. That's the other angled flame you're seeing. So you know, but this one here on the left, that's flame impingement. What should the flame look like to the eye? Well, for the most part, flame should look blue with slight orange tipping and stable. Okay, the orange drawn into the dust is typically the result of dust particles drawn in with the primary air. But there should never be any yellow tipping of a flame. Okay, Now you get into some old boilers, they could actually have a golden colored flame. It's called a carbon luminous flame, and it's different than a yellow tipping flame. Yellow tipping is a result of insufficient primary air. A bright orange flame is typically orangey goldish colored flame is carbon luminous, and it's a carbon luminous flame gives off about 6 times more radiant heat energy than a blue flame. Even though the blue flame's hotter, it doesn't give its radiation away through, or doesn't give its heat away by radiation. It gives it away, by convection. Basically, the flue gas is scrubbing the sides. So, well, that's really on old stuff. For most of the modern equipment you're going to see today, blue flame with maybe some slight orange stuff in it, and that's just dust getting drawn in. When you look at that heat exchanger, this is a failed heat exchanger right here, and you can see right here I'm circling this this crack right here. I mean, that crack doesn't look like anything that's that bad. You look at it, well, it's just a little crack in the heat exchanger. Well, when that metal heats up, who knows how far that's going to open, right? And this rusting and this staining we're seeing on this thing, that's all indications that there's spillage problems. The flue gases are going into the space instead of going up inside the heat exchanger. When I look for cracks and failures in weld, stainings, holes, pitting, the hole that we're seeing in the center right here, oops, down further, sorry. This hole right here is actually the screw hole where the cover went on, but all that rusting and staining is indicating that we have combustion dilution ventilation problems. Cracks can leak in as often as out, if not more so. Well, a lot of times on modern appliances, we have a draft inducer motor, right? And everybody says, well, you got a draft inducer motor on there, so it's going to suck air and it's not going to let CO out, right? And you think, well, heck, that's not a problem. Well, it absolutely is. It's a huge problem, because if you remember earlier slide, we talked about secondary air, and that secondary air is drawn in right by the burner. So it's drawn in at the point of combustion. If I have a crack in a heat exchanger and I'm pulling in my secondary air through that crack downstream of the point of combustion, I'm not providing that secondary air to the burner. It may be still going through the heat exchanger, but it's not getting supplied to the burner. And all of a sudden I don't have the secondary air that assures complete combustion, and I got a furnace with a crack and it's making CO. So when you get a furnace that's making large amounts of CO and you can't figure out what the heck's causing it, you check the burner, you check the orifices, you check the alignment, start looking for a crack, because you're probably pulling in the secondary air downstream of the point of combustion, and you're starving your flame for the oxygen that it needs to burn completely. All right, chemical test, the O2 test. What we're watching here, we talked about the crack can leak in as often as out, if not even more so. So what we're talking about, we start the furnace up. We start with the blower off. We watch for the oxygen and the flue gas to stabilize, right? So it gets down to like 6, 8, 7%. When the blower turns on the furnace, the main furnace blower, not the induced draft motor, but the furnace blower turns on, it's going to start to pressurize the ductwork, right? That pressure is pretty high pressure in that duct system, and it's going to force air through that crack into the heat exchanger. If our O2 starts to increase, there's a high probability that you got a crack in that heat exchanger, and you can repeat this test to verify. You always want to try and visually find that crack, because sometimes on some older appliances you may have service ports or service holes in the heat exchanger, or maybe you just have a panel that's not put on properly or a blower that's not installed properly, and it's forcing air into the heat exchanger. So we always want to try and find that crack, and once we know visually that we found it, well, then we found the problem and we can condemn the furnace. All right, this is an interesting one, because you'll run across this periodically, and we talked about the flame starving for air, right, looking for air. This is blockage of the heat exchanger. So this is a bird got down on top of the heat exchanger cell, and it's blocking the cell off when the furnace starts up. If the flue gases can't exit, right, if the flue gases can't exit, it's going to come out the front looking for air, and that's exactly what happened here. All right, some facts on cracks. Just because you have a crack or a hole in a heat exchanger does not necessarily cause the CO. It could, it absolutely could, but it doesn't necessarily mean it will. So you can't tell a homeowner, oh, you got a crack in your furnace, you're going to get CO poisoning and die. Well, no, that's not necessarily true. What it is a pathway for flue gases to mix with room air. And it's also, obviously, could potentially make the CO in the appliance. So again, any crack is a failure. Shut the furnace off, tag it off, have them contact the heating contractor if you aren't one. If you are a heating contractor, congratulations. Hopefully you just got a contract on a new replacement job. But cracks can have the appearance of, corrosion, discoloration, mineral deposits are all signs that you could have failure in the heat exchanger. So you want to start looking, because that cracks change the flame characteristics. When the flame characteristics change, it's going to affect the operation of the burner in that cell. Cracks can have the appearance of rust lines. Cracks or corrosions occur because of uneven airflow across the heat exchanger, clogged filters, heating, cooling down, and simply improper venting. CO testing, again, we sort of hit this slide, but I want to hit it again. Sample from entry to exit, sample around all your unvented appliances, sample before the draft diverter, and sample anywhere you may suspect CO. Other equipment that requires testing, don't get what I would call furnace fixation. Too many contractors go down there, especially HVAC contractors. They buy a combustion analyzer, and they forget there's other appliances that might need tested. The furnace is typically connected to the hot water tank. You need to test the hot water tank too. You should test the stove. You could test the dryer. You can test everything in there. And you don't necessarily have to fix it. If you're an HVAC contractor and you don't want to fix the stove, well, don't fix the stove, but test the stove. You can charge for testing the stove. You're protecting the safety of your customer. And you really do have an obligation to make sure that the home is safe, and that's what our job is. All right, compliance section. This is really for service technicians only. If you're doing BPI testing, you're not going to be doing these adjustments. So now that we've gone through and we've done all our testing, we need to test and adjust the appliance to meet the conformance of the manufacturer's setup, right? We're doing this to verify safety, to check the CO levels of draft, and verify our compliance of our installation or operation. So there's really only two types of appliances out of there. There's ones with not adjustable primary air and with adjustable primary air. And, and these appliances could be with or without a pressure switch. But, that's pretty much it. We either can adjust it or we can't adjust it. On non-adjustable appliances, there's no air shutter, right? The only thing we can do is set the fuel pressure. We're going to set the fuel pressure. You need to verify the input. That means you need to clock the meter. You need to know what the heat content is of the gas. You need to clock the meter. The directions are in with the furnace manual. And clock the meter and make sure that the input to the appliance is correct. You will find most manufacturers derate their furnaces. In other words, your 75,000 BTU input furnace is probably only about 72,000 BTUs of input. They derate them because they don't know the altitude at which they're going to be installed. And if you read the manual closely, it'll tell you need to change the orifices in the furnace to match the altitude at which it's installed at. And on like 90+ condensing furnaces, that will dramatically increase, having the correct input, the correct orifices in there, will dramatically increase the efficiency of the appliance. Because you got to remember, the air is entrained with, the primary air is entrained with the gas. When the gas shoots in the venturi, it entrains the primary air with it. The only way to change the proportion of primary air to gas is to actually change the size of the orifices. If you just increase the fuel pressure to change the input, you've increased the amount of gas, you've increased the amount of air, and the combustion efficiency will not change, right? If you change the orifice out, now you change the ratio of fuel to air. You're going to get more gas, and you're going to increase the input. It's going to lower your excess air. And when you lower the excess air, especially on a condensing appliance, now you're going to stop the dilution from happening, and you're going to condense more of your water out of your gas, and you're going to get that latent heat out of the flue gases, which is what you want to do with that 90+ appliance. After we get that input correct, we're going to adjust the blower for correct temperature rise. We're going to verify proper operation of the safeties, and that would be the limits, the pressure switch, the spill switches, and the pilot. If you have a pilot, you have to do, and we're talking probably larger commercial boilers here with pilots on them anymore today, but you got to do the pilot turn down test, which simply means that the smallest pilot that'll hold in the pilot safety also has to light the burner within 2 seconds, right? So 1/1000 or 3 seconds, excuse me, at 1/1000, 2/1000, 3/1000. If that burner's not lit, you need to shut the gas off immediately, or you're going to have an explosion if it does light. But the pilot safety needs to be adjusted so that it'll shut off, because the pilot's too small to safely light that burner. All right, if we have an adjustable appliance, and we're talking about one that's got adjustable air shutters on it now. Verification of the proper operation of the adjustable combustion air proving switch. Oh, excuse me. It's the same as non-adjustable. And now what we're talking about, I apologize, backing up here, is we are going to adjust the pressure switch, and that's what this slide's about. Let's say you got a power burner on a natural gas boiler. What we're going to do is we're going to slowly block the inlet air. And I'm going to just flip the next slide here, and I'll show you in a slide here. So what we got here is a power burner on a boiler. And you could actually run across this in residential. This is only a 300,000 BTU boiler. You get into a big house, a little mini mansion, you could run across this without too much trouble at all. It's wouldn't be uncommon. You're going to partially block. You can see right, it says partially block here. That's the inlet combustion air on there. And I'm going to watch the CO air free on the meter as I'm blocking that off. And when that CO air free starts approaching 100 parts per million, I'm going to adjust the switch so it cuts the burner off, right? I don't care about anything except that burner not producing CO. That's what that pressure switch is for. So if the inlet gets blocked and the CO rises, it's going to shut off. If the fan gets dirty and the CO rises, the burner is going to shut off. It's watching for the amount of air that is going into that appliance. That's what the pressure switch does. If the flue gets blocked and it starts to pressurize the appliance, it's going to shut off. So that's what we're setting that pressure switch for, is for the maximum allowable CO in the appliance. Now in this case, this is a commercial application. I'd set it to 400 ppm because it's for the ANSI standard. And in a commercial application, hopefully you're going to have somebody that's testing the appliance more than yearly, because you have a service contract on this or whatever. Somebody's doing a monthly test on this appliance. And when we have that kind of testing being done, we can definitely tighten up that excess air reading a little bit more and do it safely. All right, so combustion air adjustment, you set it to the manufacturer's stack O2 reading. If it's not specified, set it to 2 times the oxygen level, measured at the pressure switch cutout setting, but never less than 20% excess air, okay? So simply cut out at 10% O2. In other words, if the, what was I going to say here? If the, when you're setting up this pressure switch, if the cutout was 10% oxygen, in other words, you start dialing it back, you have your combustion analyzer on there, you're blocking it, and at 10% excess air, your CO starts to rise, right? Set the air shutters at 20% excess air. You never, 20% excess air is pretty much the bottom end on a commercial application that we would want to see for safety. You're always going to compromise some efficiency for safety, but you got to have that cushion of safety in there, because the burner is going to get dirty over time. So you need to have enough excess air that we can be assured that we're going to have safe combustion, through the entire setup. All right, consistency, and I think this is probably the most important part of the whole presentation right here. And so I want to make sure you guys get this piece. Consistency. We talk about consistency. What we're talking about is safe, stable combustion, draft, in flames. Okay, and what that means is, here's a normal operation. This is a Testo 330 graphic analyzer, and I shot this graph. And I did it through a whole combustion test so you could see what's going on here. And I want to go through this. I want you to pay close attention, because, like I said, this is probably the most important part of the whole presentation. And this is why we test all appliances, even non-adjustable appliances. So let's start off with a blue line right here at the top. You can see that's O2, right? That's right here at the top is oxygen. We started off at 21% oxygen, right? And start the appliance up, and the O2 level is going to drop, right? As soon as the burner lights, it starts consuming air. Now that O2 level dropped down to about 8% oxygen, and then it started to creep its way back up. Now here's the interesting thing here I want you to see. When the furnace first lit, it had excess gas that didn't get lit right away, and it lit with a little puff, you know, because all the burners don't light at once. And that excess fuel resulted in consuming the oxygen, an excess amount of oxygen, for just a split second. And then that O2 level came up and stabilized. Because we had excess fuel, if you look down at the green line on the bottom, we also had about 100 ppm of CO at light off, right? Excess fuel, excess lean on the air, and we get the little bit of CO. And that air is really not lean. 8% is pretty good amount of air going in there. Now the pink line is our efficiency. Excuse me, sorry, it's not efficiency, stack temperature. The pink lines are stack temperature. You can see when the furnace lit off, and it was about 100, went up to 150, then it started coasting up there, and the stack temperature really, it never like stabilized flat, and it's not going to stabilize flat because this was a atmospheric draft appliance, and the space was warming up, so we're going to see the stack temperature go up, and that stack temperature go up also because space temperature is rising. That's where it's getting this combustion air from. And the top line is the efficiency, which, once this thing lit, at first when it lit, the stack temperature's cool, right? So it's showing that little bit higher efficiency, but then it flattens out, and it's running right, 80-some%, right? 80-some% standard draft, non-condensing appliance. That's what we'd expect to see. Now, here's what I want you to realize here. O2, look how flat that line is. Nice flat line, right? CO, flat lined. Efficiency, flat line. Stack temperature, for all intents and purposes, flat line. This is safe, stable, normal combustion. Now, take a look at this next slide. This is combustion, dilution, ventilation, air problems. Look at our oxygen. Let's start with oxygen again. Now, this is not from a startup. This is running, so the appliance is running. Take a look at my O2 here. This is crazy. O2 is going up and down, right? It's not consistent. Not like the last slide was. It's bouncing all over the place. And that O2 is changing because my combustion air is being affected by the dynamics of the room, right? Now, I'll explain to you exactly what it was in a minute because it's interesting. This is at LMHA, which is a housing authority in Cleveland. So went out there with a contractor having trouble with nuisance trips on the boiler pressure switch on this appliance. It's a 90-plus boiler, right? So you can see right here when that oxygen level all of a sudden dropped down to 8, all of a sudden this boiler went from 0 ppm CO all the way up to 3,500 ppm when I pulled it out of the stack, right? And that's why my O2, the blue line, goes up to 21% again. Because all of a sudden I looked at my analyzer and it's going up to 3,500 parts per million. I'm like, oh, crud, I don't want to ruin the cell in this thing. So I grabbed the probe, pull it out of the cell, and the CO drops back down because it's in fresh ambient air. The O2 goes back up, right? But what's happening here is I had an elevator in a building that they had taped off the upper part of the shaft to do some repairs on the elevator. So as the elevator is going up and down in its building, it's acting like a giant plunger. And when it would go up, it would depressurize the basement, suck all the air right out of the combustion air zone of the basement, and the boiler would go into a negative, boiler room go into negative pressure, and the boiler would trip the pressure switch. In this case, again, the contractor adjusted the boiler till the pressure switch would stay in. And then when the boiler would come back, the elevator would come back down, it repressurized the room. So what we're seeing is, the elevator's going up and down a couple floors. All of a sudden it went up to the top of the building, and the O2 level dropped down to a point where it affected the combustion enough that it actually started to make massive amounts of CO. Now, this was in a commercial application. The same thing can happen in a residential application. Shutting the basement door of the furnace room should not affect the combustion of the furnace. Turning on the bathroom exhaust fan should not affect the combustion of the furnace. When the blower starts in the furnace, it should not affect the combustion of the furnace, right? That furnace should be stable and consistent the entire time we're testing. If you're seeing O2 fluctuating, draft fluctuating, stack temperatures fluctuating, you've got combustion dilution, ventilation, air problems you have to address. Guys miss this all the time. The issue is it may not be producing CO. Maybe your O2 never drops down far enough to even make CO. The question is it going to get into conditions that it can? And so what this is telling us is that you're on the fringe. When you're operating like this, you're on the fringe of catastrophe, and you need to figure out what's causing those problems. Okay, if you're a BPI contractor, you know, you need to get a hold of a heating contractor out to take a look at this. If you're a heating contractor, well, you got to start looking. Do we have enough combustion dilution ventilation air in the basement? Do we have a confined space? Do we have a blocked inlet pipe on our appliance? Is the venting system sized properly, right? There's all kinds of things we have to start looking at. But these are key indicators there's a serious problem. All right, there's a bunch of stuff here we're gonna skim over in these slides. I want to make sure we end on time so we don't run you guys late. But a lower falling O2 can be caused by obstruction of the heat exchanger cells, a blocked vent, blocked flue liner, or anything like that. Recirculation of the flue gases. Basically, if the oxygen can't get in, the O2 is going to fall. If the flue gases can't get out, the oxygen is going to fall. So you need to look through those things. You get copies of these slides so you'll be able to review this in a little more detail. A higher rising O2. Well, air leakage into the heat exchanger after the point of combustion. And again, this can be extremely dangerous when it robs the cell of secondary air and causes formation of CO. A higher rising CO. Everything is the same thing as a falling oxygen. Eventually we run out of air, we're fuel rich, we start to have all the same problems. So the blockage of the heat exchanger, collapsed liner, recirculation of flue gases. On oil furnaces, excess primary air quenching the flame or cooling it down. Flame impingement, which means the flame's actually hitting something in the furnace that it shouldn't hit, and it's cooling the flame down. A lower falling CO, that's desirable, right? When the burner lights, the CO should fall. No CO is perfectly normal. Don't panic when you don't see CO. You don't have CO with every combustion process. I've seen tons of gas furnaces and oil furnaces that produce no CO when they're operating properly. If you have a falling CO, one thing to look for is delayed ignition, because you may have an issue with a crossover that's getting dirty, or the burners aren't aligned properly, and it's causing an excess amount of gas or oil to enter the combustion chamber, you know, and you're getting a little puff back. So that's something you want to check. Fuel oil, if we're talking oil hitting the refractory until the refractory heats up, you know, it's not burning all that excess oil off. After drip of oil, it's after the burner shuts off, there's oil dripping out of the burner nozzle, or fuel delivery problems. Those are all oil related. Higher rising erratic stack temperatures. All right, and stack temperatures, believe it or not, sometimes you'll pick up problems with stack temperatures before you're picking them up with the O2 sensor, because the thermocouple is extremely sensitive. When the flue gases, when they start to back up in the heat exchanger or get drawn back in the heat exchanger because the combustion air zone is depressurizing, it's gonna start to cool down those flue gases, and the stack temperature will start to drop. And if the stack temperature is going up and down, you know, change it by like 10, 15 degrees, you probably have something going on with the pressures in that combustion air zone. Take a close look for that. Air leakage around your combustion air probes, another problem I see. When people find these erratic stack temperatures, a lot of times it's because they're not testing properly too. There's a cone that comes with your combustion analyzer that if the hole is bigger than the probe, you need to screw in so that you don't suck air around the analyzer shaft itself. Okay, you can also get high stack temperatures from lower insufficient heat transfer, right? The heat exchanger's got soot in it, or it's got, in case of water, it's got some calcium buildup or something on there. Could be overfired, or wrong size orifices, too much input, you got to caulk the meter. Could be low airflow or a low water flow, right? The heat's got to go two places, either in the house or out the stack. So if it's the water flow or the airflow is too low, it's going to be excessive stack temperatures. Soot or rust between the cells, right? It is an important note, though, with non-condensing appliances, you have to have a certain amount of heat going up the stack because you got to keep the water vapor and the flue gases vapor. Otherwise, you're going to get condensation and get damage. Lower falling stack temperature, underfired, low fuel pressure, too much airflow or water flow, high amounts of excess air, burner's not adjusted properly. Lower decreasing draft. Well, low draft is typically caused by too high of an outdoor air temperature in the summertime. That's very common. Vent connector blockage, vent blockage, undersized chimney. That's very typical. Guys put the wrong size flue pipe in or wrong size chimney in. The vent's not, the vent installation is screwed up. It's too small or not the right height, or not the right height of the building. So you need to look at the venting tables and the vent and figure out if it's done properly. Or depressurization of the combustion air zone. And typically, these are going to result in nuisance pressure switch problems on modern furnaces. Also, depending on the type of appliance, draft hooded or draft induced, low draft may not affect the combustion, right? Because we're talking about a atmospheric appliance. The draft hood is designed to separate the appliance from the draft. So the combustion may be fine, but you're spilling all the flue gases into the space. So remember, good combustion will produce little or no CO. And with a natural draft appliance, it's better to let those flue gases spill into space than it is to create a fire. So that's what the draft is, the whole idea behind the draft hood. All right, excessive draft, oversized chimney, high stack temperatures, improperly adjusted power vent, commonly results in excess heat going up the chimney, right? And that could be excess heat from the flame or excess heat from just too much dilution air going up, and you're taking the air you just paid to heat right out of your house. Step 7, we're going to test out under worst case conditions. So we've gone through all our testing. We've adjusted the appliance. Now if you're a heating contractor, if you're a BPI contractor, this is your final test and you're all done. You've adjusted the blower speed, you changed the fuel pressure, you performed the combustion test with all the panels and covers installed, ductwork's air sealed, weatherization's done. We want to do a post-test and test out and make sure that appliance is operating safely. All right, efficiency testing. If you download the Testo combustion guide, which is free on our site, if you just search for a combustion guide, you'll find it. It goes through where to test all these appliances and how to test them all. But atmospheric draft, the key thing you got to remember is you got to have an undiluted flue gas sample. You've got to sample in undiluted flue gas. On a condensing furnace, it's a positive pressure in the flue pipe. That hole has got to be sealed, okay? So typically what we want to do, if it's sidewall vented, is go outside and do the testing from the outside. Now, if you're a BPI contractor, they're probably not even allowed to test this if it goes through the roof because they don't want you drilling a hole in the flue pipe. And if you run across that situation, get a heating contractor out to do the testing with you, because leaving an appliance untested is just negligent. So you really need to get that thing tested. And typically what I'll do is drill and tap the flue pipe and put a 3/8 brass plug in there, and screw a plug right into the PVC. Pipe plugs are tapered, so it'll go in and seal just fine. And really, you can drill a hole and you can just tap the plug right in. The brass plug will self-thread right into the PVC. So that's typically what I'll do, and that way I have a sealed plug when I'm done, and then I can take that plug out, put my combustion analyzer in, do my testing, put the plug back in, and I have a sealed flue pipe. Okay. Typically, we always recommend you check with the local jurisdiction of having authority on how they want that done. And basically, that's a cop-out by us telling you that, I'll tell you the way I do it, but your building department may want you to do it another way. So if you don't know, ask. If you can't get a good answer, well, then do what you think is right. But if we're talking a metal flue pipe, you're going to seal that hole up with high temperature RTB is probably the best thing to do. All right, so you don't want to leave that hole open because it'll vent flue gases into the house. You're going to CO test outside if at all possible. All right, testing type B vent. It is okay, and it's not a violation of local code to drill a hole in a B vent. You guys have probably all heard, oh, you can't test B vents, and can't do it. The inner sleeve hole, here's what you got to do. You got to drill 2 holes. One hole is through the outer sleeve, which is just like a protection sleeve to keep the thing from catching stuff on fire. And the inner hole is what's sealed. After testing, the inner seal hole must be sealed with high temperature non-hardening sealant, high temperature RTV. Then seal the outer hole with high temperature non-hardening sealant or a patch of aluminum tape. Now, Bob Dwyer went through and actually contacted, and Bob's with CEUS, contacted every manufacturer of B-Vent, Metal Fab, Simpson, Hart, Cooley, Sealkirk, and we believe we have copies of these letters if you need them, that that B-Vent can be drilled through and tested and how it needs to be sealed. So these things are available if you need them. All right, testing boilers. Again, we've got a bigger stack, so 1/3 to halfway in the stack, find the hot spot, right? We're going to tune it for maximum combustion efficiency. This is almost a whole separate class. I don't want to get into big detail on this, but typically we're adjusting that thing for the lowest excess air possible with with some factor of safety built in there, but we're trying to tune it for efficiency more than safety. Typical combustion readings, all these are in the combustion guide, but oops, back up a little bit, sorry. Typically, on atmospheric, we're looking for an O2 level of 4 to 9%. Stack temperature is going to be 325 to 500. Draft, about 2/10 of an inch of water column to 4/10 in the stack. CO, always less than 50 ppm undiluted. It shouldn't have any problem with that. I've actually seen atmospheric gas appliances run much better than even 80 or 90 plus furnaces we have today. Don't think because it's old it's not safe. Couldn't be further from the truth. A good atmospheric appliance will run just as good, if not better, than some of the newer stuff that we have. Gas-fired power burners. Again, now this is probably a commercial application. We're talking something that's going to run a little bit higher CO undiluted, all right, because we're tuning it for efficiency. So we're going to have a lower oxygen content at 3.8 to 6%. Could be as high as 13%. Again, 275 to 500 degree stack temperature because we've got to keep the water and the flue gas as water vapor. And we're going to have that little bit higher CO. Oil burners, 4 to 7% oxygen. A lot of oil guys use carbon dioxide, so you're going to be looking for a CO2 of 10 to 12.5%. Stack temperatures of 325 to 600. Draft is 0.2 inches over the fire and negative 0.04 before the barometric damper. Oil does make CO, just like gas, so that CO should be under 50 parts per million undiluted. Smoke test, another sign of incomplete combustion, especially on oil, is a smoke. So a 0 smoke spot is recommended. Greater than 1 is not recommended. So in smoke spots, visual comparison, they do have digital meters that'll do that, which make it a lot easier, and it'll give you smoke spots to the 10th. Combustion analyzers, they're calibrated at least 1 time per year. You should get it calibrated. They're pretty easy to service. If you do overrange your sensors, you do want to make sure that you purge it in fresh air. In other words, disconnect that probe. As soon as I see my analyzer is going to get overranged, I disconnect the probe at the analyzer because the whole probe handle is full of flue gas. So I don't want to expose my sensors to any more CO than they have been. I'm going to disconnect it. I'm going to take it outside. I'm going to leave the pump run for 10, 15, 20 minutes, an hour if I have to, till that CO gets back down to 0. Because we're flushing that cell. Those are chemical sensors. If they get saturated and overranged, they're going to need to be replaced. So you don't want to, running the pump's a heck of a lot better than replacing a cell. All right, batteries, almost all of them have rechargeables in them today, so it's not a concern of mixing them, but standard stuff with batteries, you don't want to mix them. Use new batteries. Cold storage, if you keep the analyzer in your truck all the time, I'd keep it in the front of the cab, under the seat or something where it's going to get some heat from the cab, because it does have an impact on the sensors. They're chemical sensors, so they slow down. LCD displays slow down, batteries slows down, and any remaining condensate could freeze. That could cause problems, especially in the filters. It could freeze the filters up, and you might not get anything through them. So, you know, it's not a great idea to keep them in sub-zero temperatures. High temperatures, you know, the things do melt, and keep them away from the hot stacks and stuff. The filters on most of them get dirty from the inside out. So if the filter looks clean on the outside, it's still good to use. All right. If you're using them on natural gas, you may need one filter a year, or maybe even one filter every 2 years, because there's just not any dirt in the flue gas to contaminate the filter. I do change my filters out when I see they're getting totally saturated with water, just because it slows the reading down on the analyzer, and I like it to read as fast as possible, just because, I don't know, I like it. But you don't have to change the filters out. But what I'll do is pull the filter out, put a dry one in, throw the other filter in my box, just let it dry out, and then use it when I, you know, use it the next time through. Probes and thermocouples, again, you don't want to expose those to, or the temperature, the probe. You got to make sure the thermocouple centered in the probe. Make sure there's no mechanical damage. You don't want to strain the cord of the wires. You know, you don't want to carry the thing around by the probe. You don't want to make sure you're carrying it by the analyzer body. Check your hoses periodically to make sure there's no cracks or holes. You can leak test the analyzer. If you're an HVAC contractor, you have access to nitrogen. We test them. We bring them in the shop. We actually just take a like a vinyl tube that's a 1/2 inch in diameter, you know, that a probe can slide into, but the nitrogen can flow around. We'll slide it up on the bottom of a nitrogen regulator, just crack it so we get just a trickle of nitrogen out, like you'd use for brazing when you're doing copper tubing or something. Put the analyzer in there, and because it's pure nitrogen, the O2 should go down to 0, right? And if it doesn't go down to 0, if you're getting oxygen in there, that means you got a leak in your probe or in your connection, your analyzer, and you're sucking in oxygen. It's diluting your flue gas sample. So just an easy way to test for that. If you don't, you know, send it to us for a calibration verification, and we can test that for you. Pumps, they hardly ever break down, and the Testo ones are serviceable. You can actually take it out, take the pump apart, and they're just diaphragm pumps, so they're not hard to change, but the failure rate's almost non-existent. Printers, same thing. Fresh batteries. Make sure you use right kinds of paper, because if you buy the cheap paper from Staples or something, it's not a long life paper, and it'll turn black over time. So you don't want to use the office supply brands. Get paper designed for the analyzers that last up to 10 years. And then use your head. Read the manual. Familiarize yourself with it. And, you know, if you get unusually high O2s or low CO2 readings, it's likely a sampling system leak. You know, but don't lose faith in the unit. They're real easy to understand. So hopefully that they got everything for you. Sorry, I ran a couple minutes over there. It's 7:12, but I think we got it all out of the way. I'm going to open up the lines here real quick and see if I can get this open and see if we got any more questions. I didn't see anything come through on the